To give you a quick context of where Zipline stands, we should take a step back and look at the machine learning workflow of a data scientist. So you start with a business problem and you try to find data and turn them into features and then go about training a model, right? And you keep doing this in some sort of a loop until your model shows good performance offline. Now, once you have this training phase done and a good model, you try to move on to serving that model or to put it in production in some sense. So you need to serve the features in some sort of a feature store and you need to serve the model. And then the application consumes these two things, puts them together and starts using those predictions for different use cases. So this is a really elaborate process and it's a multidisciplinary problem in some sense. So turning raw data into features is something that a data engineer typically does, and using those features and generating the model is your math PhD or data scientist. And then productionizing them is a systems engineer of some sort who sets up the database and then also creates the model serving fleet, right? So the problem Big Head in general is trying to solve is making this large path. So if you look at this paper from Google, it basically claims that about 95% of the work that you need to do is gluing together different systems to serve this model and features, right? So, and about 5% is the actual ML code that a data scientist needs to write and solve for the business use case. Now, in that context, the goals of Big Head are basically enable the data scientist to do it all. So eliminate the need for a data engineer and need for systems engineers. And do it with best practices. So releasing models is a bit tricky. It's a bit more complex than releasing general software. We'll talk about that in the rest of the slides. And also make it efficient. So generating these features and models is really compute intensive and time intensive. So make this efficient and also save time for the data scientist. So basically, the goal is to automate the 95% that I showed in the last slide. So in this context, Zipline deals with the feature engineering side of things. So why is feature engineering hard? So in our survey internally, at least about 60 to 70% of the time you spend is on feature engineering stuff. And like Prasanna mentioned in the intro, a good data with a simple model is better than bad or inconsistent data with a really complex model. And this is shown time and again. So for the longest time, the Google Gmail spam filtering is a really simple naive-Bayes model. They just had enough data to classify what's spam and what's not. And the other thing that makes feature engineering really hard is that your data is not static. So when you do a Kaggle competition or whatever, you have a neatly ordered CSV files. But in the real world, data doesn't look like that. It's very dynamic in the sense that every day new data keeps arriving and through Kafka and through Hive. So the real hard problem is to incorporate that data into features. So before we talk about rest of feature engineering, here is a quick primer to data warehouse. So the actual real data, it starts from your service fleet and production database. And this gets into this message bus land as event streams and gets logged as event logs in data lake. So message bus is, for example, Kafka, and data lake is your Hive, which is on top of HDFS or S3, just to give you an example. And similarly, for production databases, there is a change stream or the mutations or bin log. Then there is a corresponding change capture log. And similarly, there is a database snapshot. So in some companies, they call this DB exports. So it's a midnight snapshot of the database that lands in your warehouse. Then there is derived data. So a bunch of other teams and a bunch of external data sources merge together in interesting ways to produce some derived data. So, and then there is media. So your images, audio clippings, videos, whatever, the unstructured data in some sense. If you look at this picture closely, we're going to consider two groups of data in particular, your service data, so the event stream and the event log, and your database data, the change capture stream, the change capture log. And so I'll call this change capture mutations interchangeably in the rest of the slides. Forgive me for that. And then there is your database snapshot. In the whole setup, what is probably new for most of you in this talk is the change capture stream and change capture log as first-class citizens in the warehouse. But it's an emerging pattern, and it's really important for leveraging real-time data in general, not just in the context of machine learning. And then there is derived data. So it is important to note this because there are some data sources in a company that cannot be real-time just because you're joining with various external data, and there are transformations that are opaque to you that you cannot replicate in a real-time setting. So this is going to be midnight accurate or snapshot accurate in some sense. And where Zipline doesn't help is with media. So if you are extracting features from images or audio or whatever into embeddings, if that is the only thing that you're doing, then Zipline isn't really necessary. So let's start with an example. Let's say I'm trying to recommend a restaurant, and I'm making up some really bad features. So the first feature here is the total number of visits to that particular cuisine in the last month and the average rating of the restaurant in the last year. So the observation here is that most features are aggregations, right? So I just expanded the last slide to show what those aggregations are. And to put it in the context of the slide before, where we talked about the data warehouse structure, the first thing is total visits to the same cuisine last month. So it's a count of visit grouped by the cuisine and window of 1 month. So we are saying that there are two things here. One is the check-in stream. The other thing is the check-in log, and the stream being in a message bus or Kafka and the log being in Hive. And this is another example where the second example, which comes from the database side of things. So there is a ratings database somewhere, and it gets snapshotted into Hive every day, end of the day. And then there is a mutations stream. So for for some of you who's not aware of the mutations story or change data story, there is this neat little tool called Debezium that you can slap on your database to extract the mutations in real time. The tricky part is leveraging these mutations into computations, and that's where Zipline comes into play. So these are some real Zipline examples. So you specify, so it's pretty much what I showed in the last slide. Instead of, putting it in SQL, we kind of hijack the aggregation side of things for reasons you'll see later. And we let you specify almost the same thing. So you'll say, what's an event stream, what's an event log, and what's the query. And you specify what are the keys. And you specify the aggregation. So there is a way to specify the windows, and you can document it too. And similarly for the database source. Right, let me not dwell on this too much. And at the end of it, you say all of these features are now joined together to create this feature set. And we call it a left outer join, but in some sense, this is the larger feature set API. Right, so before we go into how all of this works internally, let's take a step back and understand how this data is computed. So visually speaking, let's say I wanted to predict or recommend you a restaurant. At some point in time, a label arrives to me, which basically is from the check-in stream. It tells me whether you went to that place and gave that place a good rating or not. And meanwhile, there are features that keep changing, which is the average rating of the restaurant or how many visits you had for that particular cuisine in the last year. So at the end of all of this prediction stuff, you log it to create training data set. Right. And similarly, if I were to predict at another point in time when you check your phone again, for example, then the features change and the aggregations over those features change, and then you create another row with the same label. So if you look at this closely, this is some sort of a join with the feature data and the labels or prediction times. And while joining, you're also doing a few aggregations. So this is why it's called a temporal or time series join with aggregations. So we're going to quickly look at the feature serving side of things and jump into how we actually compute this before you even serve. So first definition of feature serving is what is the value of these features at this point in time right now. So the problems here are this needs to be optimized for reading, optimized for point queries. And there is a subtle difference between freshness and latency. Freshness is when it's real time. Latency is how long does it take to read. And you achieve freshness by incorporating the Kafka data or service events and DB mutations. We will talk about why we need batch corrections as we go through the rest of the slides, but that is a pretty important detail as to why the design is in a particular way. So to recap all of that again really quickly, there is fact style features and dim style features. So if you remember, the check-in stream is fact style data and the ratings table is some sort of dim. So you could argue that it could be fact too, but most companies, they store ratings tables or reviews table as a dim table in some sense. And you put them together. So you put the change stream and the dim snapshot to create the other group of features. And in the first case, you just put together the fact log and the fact stream, which is the most common pattern. So it's aggregations over service events to get real-time features. So the serving architecture in Zipline is pretty straightforward. So you start from that definition that I just showed you of the join and the group bys. And the feature store basically has two parts, the batch side of things that comes from the warehouse data and the streaming updates that comes from Kafka. So we use Flink to generate the streaming aggregates and update the feature values. And then there is a model server which serves these features to the model and generates predictions for the application. So there is a color coding here. All the blue things of various shades are related to Zipline. And so feature declaration is something user provides, and Zipline generates the pipelines that create streaming aggregates and batch aggregates that update the feature store. And there is a Zipline client that is embedded in the model server, which is read by this model, which is in green. The green color coding is basically big head. So it's the non-Zipline part of the project. And then the purple thing is user-facing things. So if an application engineer wants to embed these predictions into his application, you just make a call to the model to get the prediction. So this is your typical Lambda. It's nothing new, but we'll see how aggregations make this Lambda a bit more nuanced. So there are two ways to go about actually. So the first thing is we are now able to serve features. So the second thing is how do we compute those features for training? Because training comes first, right? It's not serving. One way to go about these features is to actually log them. You created this serving infrastructure, and as you serve, you just log the new features that you want without actually using them into the model. It's really easy to implement. It's really consistent. But the real kicker is that it takes a long time to gather enough data for your new feature to create a new model. And sometimes, so based on what kind of business you're in, for something like Airbnb, you need to capture seasonality. And that will mean that we'll need to wait for about 6 months to 1 year to actually generate decent data to create a good model. So our goal here in Zipline is to, instead of relying on the log and wait approach, instead compute the features as if you log them, so with full consistency, without having to wait for a year's worth of time. So in that context, the definition of feature computation is, given your feature definitions that I showed you in the previous slides, what are the exact feature values at various points in history, right? So let's say this, I'm taking the same example. So there is a user and a restaurant that I want to recommend. And there are different timestamps at which the user checked their phone to look at the recommendation or whatever. And given the query log, this query log, and the definitions automatically fill in the right side. Right. So before we go into the final topology of how that aggregations work over Spark, let's do a simple intro to the aggregations themselves. So some aggregation has a nice property. Some is basically adding two things. It is commutative. You can reverse the order, and it's also associative. You can break up a series of sum of n elements into smaller chunks arbitrarily, and you can compute them partially and add them up later together. And another interesting property is that it's also reversible. Let's say events fall out of your window or whatever, you can just subtract them, right? And in category theory terms, this is what's called an abelian group. So average also has similar properties, especially if you factor the intermediate, if you create something called an intermediate representation and maintain sum and count separately, and at the end you do the division. So it's not a breakthrough idea yet. And one additional constraint that Zipline adds to these aggregations is that it needs to be constant memory or bounded memory. So there are two classes of aggregations actually. So what we showed, some average count, etc., have this reversibility property, but min, max, and some approximate unique counting using hyperlog log or whatever don't have that property. So again, some category theory terms, but the real difference is that one group, the first group, sum, average, and count, is reversible, and min, max, approx, unique count, etc., are non-reversible. So you cannot delete elements that fall out of a window if you just maintain the aggregate, right? So just to demonstrate or like visualize what I just said, let's say you want to compute visits or check from the check-in stream of a user for the last year. As the window slides forward, you just need to subtract the elements that fall out of the window and add what came into your window. So 0 comes into the window, 1 falls out of the window, and you can simply update 8 to 7. So that subtraction is really key in us being able to do this sliding effectively. So how do we do this with irreversible aggregations like max? So one interesting observation is that as the window slides, we really don't need to look at all the underlying elements, because before the window slid, it did some aggregation, so we could somehow reuse those aggregations to compute the new window. And one way to exploit some of that structure is to impose a binary tree of sorts. So I just cache the intermediate values of in the binary tree. So in some sense, to slide the window forward, I need to look at certain specific nodes and sum them up together. And if the nodes don't exist, just compute them and store them. So we're trading off some space for getting the speed. but we are basically trading off logarithmic. We are achieving logarithmic time instead of linear time by trading off linear space. So this is basically some table of where we really need those aggregations. So if it is reversible and if it is unwindowed, if it's unwindowed, you don't need the reversal. But if it is windowed and if it's not a reversible operation, you need the tree logic. And another context where reversibility comes into play is change data. We talked about how we can use change stream or mutation stream from a database to create real-time features. So the database change stream has updates or deletes, which basically translate to us having to do reversals. So in some sense, let's say a review gets taken down, so that rating value needs to be subtracted from the average or reversed from the average. Right. And that's the context where reversibility also comes into play. And this is the reason why to incorporate reversibility or incorporate mutations, we need to give different guarantees for reversibles versus non-reversible aggregations. So going back to our example, I'm just putting this here before we go into the next part of the slides. So the left side is query log and the right side is the final output that we want to compute from raw data. So in that context, a feature backfill has this structure. So the left side is the query log, the right side are the events, and the output is the aggregated features. And the schema of the left side, I'm simplifying a lot here, is a key and a timestamp. So the new concept that we are introducing here is the key. So if we go back, the user is the key for visits, and the restaurant is the key for average rating last year. Right, and the output is aggregated by these different keys. So the keys also change. And the idea is, so one way to imagine how to do this aggregation is to roll back your warehouse data to different points in time, run the aggregations and compute the results. But that is really, really slow and intractable in some sense. That would translate to basically 2 to 3 months worth of Spark jobs, which don't exist. Spark jobs don't run for so long. They before a few days. So it's really important that we optimize these aggregations. And another observation here is that the raw data that we aggregate over is much, much larger than the query log. So the right side is really large, left side is relatively small. So we can use that to determine how we design our Spark topology. So before we go into the Spark topology stuff, let's take a simple, it's not so simple, but this is basically what what you would need to do on a single machine. So imagine the raw data and the query log are two CSV files on your machine. Now you need to take those CSV files and compute the final results given our aggregations. You would need to do something like this. It's a nested 3-level for loop. And you look at, so you do the bare join and you try to go over all the query times, and then inside in a for loop, go over all the events. And if it is in the window, you update the aggregate. Right now, this is really, really expensive because it's quadratic in terms of queries and events. Right. So and also you're passing over events multiple times, but we said events is the largest side of things. So what we do, the first set of optimizations is to actually only pass once over the events. So instead we switch the loop. So we switched the events and the query loop, and then we are doing the update differently. So here I broke the complexity down into two parts. One of them is the search and the other one is the update. So we are searching through all the queries and we are updating as many candidates with the payload in the events. And the second optimization we can do is actually reduce the search complexity. So we can do something like binary search if we assume that the queries are sorted with time. That we can do beforehand, and we can use that for all the aggregations. Right. So B search here stands for binary search. It's nothing fancy. And the complexity goes from order of queries to order of log of queries. Right. But the real problem here is actually updates. Updates are more expensive than search itself. So can we reuse that, reuse the logic that we looked at beforehand to optimize even the updates? So the idea is again simple. We invoke this tree merge thing. So as we are passing through events and as we are updating these queries, we, instead of updating all the candidates of a search result, we only update the logarithmic number of tiles that tile up the entire event span. So if I'm updating from 4 to 13, instead of updating all of these individual 7 things, I instead update only 3 things that are highlighted here. Right. So that makes the code look like this, but it's still on a single machine and it doesn't really handle the scale of data that we really want it to handle. So the next step from going from here to the Spark topology is to try splitting this out into different stages. So here, if you see, we call those intermediate things tiles, and we have these 3 separate looking stages in some sense. So there is a stage where you collapse the tiles. So you updated the intermediate nodes, but at the end of the day, you still want to generate each row for a timestamp. So that collapsing is what collapses all the tree into underlying cells. And then there is another function, which is tile range. So given a range, so in the previous thing, the range is 4 to 13. Given a range, compute the tiles that I need to update. So the logarithmic number of tiles. So in that sense, there is basically 3 stages in the topology from left to right. The first stage is basically creating the query times that are sorted by the timestamp, then doing a broadcast join. So broadcast join is when you know that there is a really small side of the join. So you just send the small side over to the large side. And when I say the large side, you're not really keeping all of that data in memory. You're just passing through chunks of that data into memory and aggregating them into the broadcasted thing, and then collapsing it finally into actual values. So these are roughly the 3 stages in the Spark topology. I won't go into too much detail here, but it's just here for the sake of completeness if you guys want to refer later. So that's basically the crux of my talk. And if we take a step back, this is what the architecture looks like. So you give me a feature declaration or give Zipline a feature declaration. It creates those feature backfills that we talked about, right? Then you use those feature backfills, collect labels if it needs to be collected separately, and then train a model. And then you go to serving, right? And then you tee it up with the application. So we talked about serving first because that's the easiest to understand and explain, but backfill happens first. So we don't log and wait, we actually compute these things.